What's poppin' YouTube? Welcome to the first video on my new channel named Collab Math, where we're gonna take you through mathematical adventures. Cue the intro. So here we have a function, and it's the derivative of f of x. So this is something basic you have to remember. When a derivative is positive, a function is increasing, and when a derivative is negative, a function is decreasing. This makes sense because derivative is a slope. So if the slope is positive, it has to be increasing. If the slope is negative, it has to be decreasing. So we're going to take this chart and make a sign chart of where the derivative is positive and negatively valued. And we're going to do that by using the points where it crosses the x-axis. So it crosses at -3, -1, and 3/2. So from negative infinity to -3, the function is negative. Then from -3 to -1, the function is positive. From -1 to 3/2, the function is negative. And from 3/2 to infinity, the function is indeed positive. And what this tells us, what does this tell us? Oh, yeah, this tells us the shape of the original function. So it's going to be going down, then it's going to go up, and then it's going to go down, and then it's going to go up again. So this can tell us that at x equals 3/2, we are going to have a relative minimum down here. And that at x equals -1, we're going to have a relative maximum. And that at x equals -3, we're going to have a relative minimum. Okay, and so then if we go to the second derivative, we're looking for points where this function turns, this derivative, this first derivative function, turns from positively sloped to negatively sloped to find the critical numbers of that second derivative. So at x equals -2 and x equals 0, actually, we're going to have this function change from positively sloped to negatively sloped, and those are going to be the critical numbers. So -2 and 0 on our sign chart for f prime prime x. So from -infinity to -2, this function, the derivative is going to be positively sloped. From -2 to 0, it's going to be negatively sloped. It's in this part of the function where it's going down. And then from 0 to infinity, it's going to be going up, so it's going to be positively sloped. So this means that if we have a positively sloped derivative, the second derivative is going to be concave up at that point. And look, this makes sense, because if our original function goes like this, it's making that same shape that we see down here with our second derivative. And if our next part is going concave down, that makes sense again, because we have a concave down part. And if our third part is concave up, that makes sense, because we've got the concave up part right there. So points of inflection, this is the next part. Points of inflection are when the second derivative changes from positive to negatively sloped or vice versa. And those are the points we're going to use for the second derivative sign chart. I don't know if I call them critical numbers. I don't know if that's right. I don't think it is now I think about it. But those are definitely points of inflection when it changes from positively sloped to negatively sloped, the first derivative. All right, that is a graphical example. We're going to move on to an analytical example next. Next, we're going to talk about Rolle's theorem. I think it's kind of dumb, but we'll go through it anyways. Okay, Rolle's theorem says that if f of x is continuous on a closed interval AB and differentiable on the open interval AB, if f of A equals f of B, then there is at least one number in A of B so that f prime of C equals 0. And basically what that's saying is that if you have a function on a closed interval where the two endpoints are the two endpoints of the interval have an equal y value. So like graphically, like you've got something like your interval would be like right there, and it starts and ends right here, and it's like zoom, there's somewhere in this function that the derivative is 0. The horizontal line. There's multiple places in this one. But that's what it's saying. It's saying there's a horizontal line somewhere in the derivative of that stuff. So first of all, you have to check if f of x is continuous in the closed interval that you're given. So here we're given the function f of x equals x squared minus 3x plus 2. So we're going to check because we're given the interval 2, 1. Is it continuous? You're goddamn right it's continuous. Is it differentiable? Hell yeah, it's differentiable. Does f of 1 equal f of 2? Yeah, they're both 0, so that's great. All right, so what we're guaranteed here is that there is a value of a derivative that is 0. Somewhere, there's going to be a horizontal line as the slope of this thing somewhere. So what we're going to do is we're going to set this derivative that we found, since we know that this is true, by saying that it's continuous on the closed interval, differentiable in the open interval, and that the endpoints are equal, we are guaranteed a derivative that is 0. So what we're going to do, we're going to make this gosh darn derivative 0. 0 equals 2x minus 3. 3 equals 2x. X equals 3 halves. That is the value of c where this occurs. So that's our c value. And if we plug that 3 halves back into the original function, we can find that exact point where the derivative is 0. Crazy, right? So that point's going to be 3 halves negative 1/4. On to the next one. The mean value theorem. It's pretty much the same thing. If f is continuous on the closed interval AB and differentiable in the open interval AB, then there exists a number c in AB such that the instantaneous rate of change at some point in interval is equal to the average rate of change. Graphically, this looks like... Okay, it looks like something like... Here's our interval. We have one endpoint that is not equal to the next one. And we're going to go like... So there's going to be a derivative somewhere in here that is equal to this average rate of change. Because the average rate of change would be this line. Because it's a slope. There's going to be a slope somewhere on this function that is equal to the slope of that line, that average rate of change, which would probably be like right there. But analytically, we have the function f of x equals 5 minus 4 over x. So we're going to plug in 1 and 4, which is our interval, to find those values, to find the average rate of change so we can set up this problem. So we plug in f of 1 and f of 4, and we get 1 and 4. Average rate of change of 1 and 4, 1 minus 4 over 1 minus 4 is 1. So if f of x is continuous on the closed interval that we're given and differentiable in the open interval we're given, we know that there's a point that the slope of that is equal to the average slope across the whole thing. So we're going to take that value that we've gotten, that's 1, and we're going to set it equal to something here. I don't really remember. Is this the same problem? It is, because we're finding the derivative of this. So the derivative of this, of 5 minus 4 over x, that 5 is going to go away, so we're just going to have 4 over x. So the derivative of 4 over x is negative 4 over x squared. So then okay, yeah. Negative 4 over x squared equals 1. So we multiply this out and we get negative 4 equals x squared. x squared equals positive or negative 2i. And what we can do with that 2i is we can plug it back into the original function, and we can get the point where the derivative is equal to the average rate of change. Because there has to be, because of this theorem, which is pretty much the same as the last theorem, just a little bit different. That's all for this lesson, YouTube. Stay tuned for more quality content, more mathematical adventure, more learning, more love. This is me signing off.